So this particular talk is going to be regarding the anatomy and physiology of the cerebellum. You have a second video that talks about the clinical features of the cerebellum, but the two together should give you some understanding of how this part of the nervous system is working. So this is the outline of what we're going to go through today. We're going to talk about the anatomy, somatotopy, blood supply, which is likely to be a review after the lab, cellular features, and then connections to the nerve axis, which really are probably the most important set of slides for step preparation. So let's just review the very basics of the cerebellum. If you look at this very simple picture on the left side of the slide, you can see that the cerebellum sits underneath the cortex and is connected directly to the brainstem. So the physical location is within the posterior fossa, and there is that covering of the cerebellum, the tentorium cerebelli, that serves as a physical barrier in between the cerebellum and the cortical structures. There is this very close, tight connection to the pons, and you will see that many of the cerebellar fibers are going to be moving back and forth between the two parts of the nervous system. So the cerebellum, again, sits below the cortical regions, and what you can see is that it has a little bit different appearance than the cortical gyrus. So you can see these folia, or these kind of lines that go across the cerebellum, and so if you're looking at gross structures, you can tell the difference and where you're looking. If you cut the cerebellum in half, you will actually see that there are divisions within the cerebellum itself, and we'll talk more about that in the next slides. So the general anatomy of the cerebellum is that it has a vermis that sits kind of right in the middle, and then these two cerebellar hemispheres. Now, we also break down the anatomy of the cerebellum in another way, and that's by lobe structure. So the lobe structure comes from the kind of evolution of the cerebellum over time. So the most primitive portion of the cerebellum is the floccular nodular lobe, and this particular lobe kind of connects the cerebellum to the vestibular nuclei for those very basic structures that allow you to stand and to kind of coordinate walking. So you can see that this particular lobe is here labeled F. The anterior lobe up in here is the paleocerebellum. We think it's the second oldest lobe of the cerebellum. And then the posterior lobe, the neurocerebellum, the most sophisticated part of the cerebellum, is located here in the back. So if we look at the appearance of the cerebellum, you can see these folia, which we've mentioned already before, and these are these kind of gyri that are located transversely across the surface of the cerebellum. Now, there are some tonsils that we've learned about already, and you can see this tonsil, cerebellar tonsil, sticking out right here. It's kind of an eminence on the vermal structure of the cerebellum, and it's on the medial and inferior posterior surface. So the issue with the tonsil and why it is so incredibly important is that because of its location, it is one of the first places that will be impacted if you have a herniation down through the posterior fossa. So what happens is that there's pressure on that tonsil, and the pressure on that tonsil leads to kind of emergency signs that we look at if someone is going to herniate. I think you've probably discussed this already in the anatomy labs. So the terminology of the cerebellum is that there are 3 fissures and 10 divisions. So here we can see on the gross structure the labeling of the divisions, and here is the cerebellum as if it were a two-dimensional structure and kind of laid out. Now, it's not that important to understand the somatotopy of the actual divisions, but to know that the cerebellum is divided differently than the cortex, and that these fissures and divisions allow us to localize into the cerebellar regions. Here you can also see the location of the floccular nodular lobe down here. Again, this is the most primitive nodule of the cerebellum. Let me just go back and mention once again that the vermis here, we want to make sure we know the difference between the vermis and the cerebellar hemispheres on the sides, because this becomes very important when we start to localize cerebellar lesions. So the anatomy of the cerebellar peduncles are that they kind of serve as this relay station for fibers in and out of the cerebellum. I kind of like to think of the cerebellum as a computer, and it essentially is kind of like the it is the organizing portion of the nervous system, in that it doesn't actually provide direct information regarding strength or sensation, but it takes all of that information and combines it with vestibular information in order to coordinate movement. So it's kind of this relay center where all of the motor and sensory information is coming in to the cerebellar structures, and then the cerebellum will process it kind of like a computer, and then sends the information back either down into the corticospinal tracts or back up into the cortex for additional processing. So the cerebellar peduncles are the location of all of these fibers going in out of the cerebellum, and they're quite important, especially for some diseases. So you can see that they're divided here into the superior, the middle, and the inferior cerebellar peduncles, and certain fibers kind of go in and out of those peduncles. So this is the breakdown of the types of fibers, and this is another picture that shows what this looks like in color coding, which makes it a little bit easier. So efferent fibers are going to be located in the superior cerebellar peduncle. So those are fibers going back up into the cortical structures. The middle cerebellar peduncle is going to be sending fibers back and forth from the pons, so the vestibular fibers and a lot of those fibers coming to and from the spinal cord. And finally, the inferior cerebellar peduncle are those afferent fibers that are coming up, also from the spinal cord and other regions. So let's turn now to imaging of the cerebellum, and what you can see is that in this particular image, this is an MRI scan, we can see the location of the cerebellum and its connection to the brainstem. Now, because the cerebellum kind of sits in this bony structure in the posterior fossa, it's very challenging to see any detail of the cerebellum when you're doing CAT scans. So I typically don't even bother to order CAT scans on my cerebellar patients. MRI scan is going to give us a much better picture of what's happening in that location. So if you kind of look here, this is a picture of the pons, and you can see this big structure sitting right between the pons and the cerebellar hemispheres. This is the middle cerebellar peduncle, so that main relay station that we learned for the pontine fibers. Back here is the cerebellum. We can see the hemispheres and the vermal area. So occasionally, especially if there's volume loss in the cerebellum, we can see the detail of the fovea, but many times if the cerebellum is healthy, you won't necessarily see that in the imaging. This is another picture showing the relationship between the gross anatomy and the imaging structures. And what you can see here is just a little bit higher up in the midbrain and kind of the top or portions of the cerebellum. Again, we've got the vermal regions, we've got the anterior lobe. We see these fissures now. You can actually see them a little bit better in this cut, and we see our cerebellar hemispheres on the right and the left. Now we go over here to our imaging. We can see, again, just this small portion here. We can see the vermis of the cerebellum and the midbrain. Now what you will notice here is that we see very good detail of the fovea of the cerebellum, and this actually tells us in this particular image that there's volume loss in this area. What causes volume loss of the vermis? Most common cause is alcohol. So you have to remember that after you're viewing these videos and going out for a drink Friday night, that you may actually be doing some damage to those cells. Now this is if we go a little bit lower into the pontine area. Again, we're catching a little bit of that anterior lobe of the cerebellum, but we're a little bit farther down. Okay, so let's move into a different cut. So now we're going to look at a sagittal cut of the cerebellum, and this is actually a really important cut to look at in my clinic because it gives me some idea of what the volume is or the health of the overall cerebellum. So here is again our gross section of the cerebellum. You can see the pons, the midbrain, and the medulla, and over here we're seeing the lobes of the cerebellum. So over here on the right, we see just a very kind of blown up piece of the central part of the MRI scan, and it's essentially compares very nicely to the anatomic structure. So here's the cerebellum back here with the lobes. You can actually see the fissures in here, the divisions, and you can see a little bit of the detail of the fovea. Now this actually looks like a very healthy midbrain, pons and medullary brainstem. So this is probably a younger, healthier person. There is a little bit of volume loss here because you can see some of the spinal fluid around the cerebellum, and if this was a very healthy person, you would not be seeing any of that. So here is another image, anatomic image of the cerebellum, and what you can see is that we're now getting a picture of the floccular nodular lobe and the tonsil. So we're kind of now towards the bottom of the cerebellum, and this is that structure that's really important to tell us if we're about to herniate. So let's talk a little bit about the somatotopy of the cerebellum. So just like the cortical areas, there is somatotopy, and the somatotopy here is that the kind of the trunk and some of the other midline structures of the body are going to be located in the vermal area. So the trunk, the eyes, again, axial sort of localization. In the hemispheres, you essentially have the arms and the legs, and so we want to kind of remember this as we're seeing patients. Now let's dive a little bit deeper into the molecular level of the cerebellum, and we essentially have some layers, 3 layers that have cells within the cerebellum itself. So the top layer is called the molecular layer, the middle layer is the Purkinje layer, and then there's the granular cell layer. And then of course you have the underlying cerebellar white matter. Within the cerebellar white matter are the deep cerebellar nuclei, and these are incredibly important as relay stations, again, for information. Now, the Purkinje cell layer is probably the most important cell layer to know about in the cerebellum because it's distinct to this area. So let's talk a little bit about the deep cerebellar nuclei, and what you can see is that I've noted on this slide that you have to know these for step 1, and there's actually a mnemonic: don't eat greasy foods. So there are 4 cerebellar nuclei. The dentate is the largest, and it is what tends to receive the pontine fibers. So you can see here it's this kind of blue squiggly structure. I think Joanne O'Keefe, who teaches neuroanatomy in our medical school, likes to say that this looks like a stuffed olive. I'm not quite sure I see that, especially in this particular cut, but you can see it looks very different in appearance to the other nuclei. It is definitely for sure the largest, which makes sense because it's relaying all that pontine information. We have the emboliform, the globus, and the vestigial nuclei as well. And those are smaller and less important, but do receive fibers from various areas. So the Purkinje cell, let's talk about the Purkinje cell briefly. This is the principal neura of the cerebellum. So if you hear Purkinje cell, then you're going to think cerebellum. Now over here is Dr. Purkinje, so the cell was named after him. We're doing this less, but again, hopefully this will remember that this is where it's coming from. This is an inhibitory cell, and the thing about the Purkinje cell is the axons do not project outside of the cerebellum. The cells do modulate the activity of the deep nuclei, and they form efferent pathways to the brainstem and the cortex. This is kind of a close-up version of what the Purkinje cell looks like, and this is it under EM. So this is the next important piece to know for step 1, and I've tried to simplify this as much as possible. But what you'll see here on the right side is the pathways coming into the cerebellum from the cortex. Now you need to know from cortex to cerebellum, and then you need to know from cerebellum back up to cortex. So let's just kind of walk through this pathway. What's going to happen is that the information is going to start in the contralateral motor cortex and the corticospinal and corticopontine fibers. That information is going to come on down, and then it's going to synapse in the pontine nuclei. Okay, so once it synapses in the pontine nuclei, it's going to decussate or cross over at the level of the cerebellar peduncles, then move through the middle cerebellar peduncle and into the dentate nucleus, which you can see located here. So once it moves into the dentate nucleus and the hemispheres, you can start to have processing of that information. The inputs into the cerebellum also include information from the spinocerebellar tracts, Makes sense, right? Because you need that information coming back up to coordinate with the motor information going down. So these are the tracts that, the most important tract actually is the dorsal spinal cerebellar tract. And this particular tract carries proprioceptive information. So we've got kind of a picture of it coming up. It is an uncrossed ipsilateral tract. So as it comes up through the spinal cord, it goes here in through the inferior cerebellar peduncle, and that information is going to move into the cerebellar hemispheres for processing. So again, important tract you need to know for step 1. Okay, so now we're going to take those tracts from the cerebellum back to the cortex. So from the cerebellar hemispheres, the information is going to originate from the Purkinje cells and then move back through the dentate nucleus. Now, because we have efferent fibers, we're going to be traveling through the superior cerebellar peduncle. You're going to have decussation in the midbrain up into the thalamus, and then after the thalamus, that information moves into the contralateral cortex. So again, this pathway is incredibly important, and you're going to know this for your step exams. So let's talk just briefly about cerebellum and posture. So you probably always wondered why, if you wake up out of a deep sleep, you can stand up and start moving immediately. Well, the reason why you can do that is because you have some very primitive pathways that are essentially created very early in evolution and have been sustained because they allow us to get up and move quickly, regardless of what's happening higher up in the cortex. So this information is actually relayed through the vermis and the floccular nodular lobe. And as you remember, this particular lobe is the oldest of the lobes of the cerebellum. The information is relayed through the deep nuclei, through the vestibular and reticular nuclei. And all of this information exerts postural control and extensor tone. So this is the system with which you can stand if you're able automatically by reflex to have extensor tone, and all of this information is running through these very primitive systems. It's going to be very easy for you to stand up and walk when you need to again. Now you can see there is some information that's being used from the cortical areas, especially the motor cortex, which makes sense because you need to have strength when you're moving. Okay, so that is the end of the anatomy portion of the cerebellum, and please now go and take a look at the clinical piece that will pull together the localization.